Hi, this is an introduction to exploiting diffusion prior for generalizable dense prediction. Image properties such as normals, depths, and segmentation are important for understanding high-level image semantics. A lot of prior work has developed many approaches, but most development and the collection of training data are in the domain of real-world images. In fact, if we test these off-the-shelf models with more diverse images, such as those generated by recent text-to-image diffusion models, these off-the-shelf predictors start to struggle, like the examples here. But if pre-trained text-to-image models are so strong at generalization and imagination, can we adapt this ability to dense prediction tasks? A naive solution would be considering the dense prediction problems as image-to-image translation. Some recent works have used diffusion models to perform image-to-image translation. However, we cannot directly apply these methods because, first, diffusion models are inherently stochastic. From the same input, models can generate different possible outputs with different initial noise. Second, we have to carefully maintain the balance between keeping the ability of generalization and learning new tasks in new domains. Specifically, the stochasticity of diffusion models derives from two sources: sampling of initial noise and extra noise added during the generation process. Some diffusion-based image-to-image methods limit this stochasticity by adding constraints on latent features according to inputs, such as injecting attention features, but this may induce unnecessary information from input images and make estimations incorrect. Some methods add guidance from input images. For example, they encode both latents and input images, or start the generation process from the inversion of input images. But taking different strengths of guidance makes the output contents inconsistent with input images. They may produce plausible results looking like other images or the same images with inaccurate estimation. For the tasks we consider in this work, we don't want any variation or trade-off between preserving contents and getting correct estimations. So, we propose a different approach that exploits diffusion models as prior for dense prediction problems. To adapt diffusion models into deterministic mappings from input images to output predictions, we reformulate the diffusion process to avoid initial sampling. We don't use the common diffusion process that destroys images by adding Gaussian noise. Instead, we adopt a blending perspective that turns output predictions into input images. The diffusion process becomes a chain of interpolations of input images and output predictions, where the importance of input images gradually increases. And the model is trained to generate estimations by taking interpolations of inputs and outputs. In other words, we can view the diffusion process as morphing output predictions into input images, and through the generation process, the model iteratively demorphs input images into output predictions. Then, to keep the generalization ability, we fine-tune a pre-trained text-to-image model with low-rank adaptation and an objective to predict v-prediction. And we can avoid extra noise added in the generation process by adopting deterministic sampling. To evaluate our approach, we consider 5 tasks of dense predictions: estimation of surface normals, depths, albedo, shading, and semantic segmentation. We train the model with images of bedrooms and test it with 3 sets of images. The first set comprises only bedroom images, which test the in-domain performance. The other 2 sets contain images of diverse scenes and arbitrary images, showing out-of-domain generalizability. To keep categories consistent for segmentation, we test out-of-domain segmentation with bedroom images generated in diverse styles. We can see from the examples here, the fine-tuned model gets high-quality and accurate estimation for both in-domain and out-of-domain samples. And for arbitrary images, though the model is trained with only bedroom images, it performs favorably against the off-the-shelf and other baseline approaches, showing great generalization ability. Besides solving the tasks, the precise properties enable many other applications to handle these challenging inputs. For example, for 3D photo and painting, if we replace the off-the-shelf depth predictor with our model, the result videos look more realistic, like these examples. Please check the main paper and the supplementary document for more details. Thanks for watching.